This is lecture number 5. Let's begin with the overview of the previous lecture. Um, in the previous lecture, I emphasized the concept of the degeneracy. And degeneracy means that when the all the if the eigenvalues of some given operator are not distinct, meaning that some of the eigenvalues are the same, then we call that such kind of situation as a degeneracy. Another important concept or another important types of the linear operator is called as a Hermitian operator. And Hermitian operator has a few interesting properties. The first property is that all the eigenvalues of the Hermitian operators are real. And if the Hermitian operator doesn't have any it does not have any degeneracy, meaning that all the eigenvalues are distinct from each other, then the eigenvectors will be orthogonal to each other. And if we use these eigenvectors as a basis, as a new basis for the Hermitian operator, then the matrix representation of that Hermitian operator in this eigenbasis will appear in the form of the diagonal matrix. Another interesting types of the linear operator is unitary operator. And unitary operator has the property that all the eigenvalues are unit modulus, meaning the absolute value of the or the magnitude of the complex number is 1. And another important property is that even if we apply the unitary matrix, unitary operator on some vector, the length of the vector will be preserved. And also similar to the Hermitian operator, if the unitary operator is non-degenerate, then all the eigenvectors will be orthogonal to each other. Finally, at the end of the last lecture, I also spent some time on the basis transformation. If we denote that matrix representation of some operator in some orthonormal basis, then I can just write down with this notation, and we can think about new orthonormal basis, which I represented here using the Roman numerals. Then there should be some relation between this new matrix representation and then old representation of the same operator omega. And then how can and the relation generally can be represented. There exists this kind of relation, and in this case, this matrix is matrix representation of some unitary operator U, and in this unitary operator is defined in this form, meaning that it is a summation of all the outer product made by the new basis and then old basis. So this is m's new basis vector, and this is m's original basis vector, and then by combining them using the outer product and then add all of them from 1 to n, then this will become the unitary operator. And then if we represent this unitary operator in terms of the old orthonormal basis, then it will appear in this shape, and then this matrix can be used to convert the original matrix representation to a new matrix representation in the new orthonormal basis. As we discussed in the review of the previous lecture, there we know that when we are given some Hermitian operator omega, then even though the current matrix representation of the of this Hermitian operator is not a diagonal representation for some orthonormal basis, we can always change our basis from this some arbitrary orthonormal basis to a orthonormal basis composed of the eigenvectors. So yeah, we call this one as the eigenbasis. And then if we represent this Hermitian operator in this eigenbasis, then the new matrix will always show up as a diagonal matrix. And then if you are wondering how to convert this H to the new matrix form, then the as I mentioned right before, they will be connected through the unitary matrix, and then unitary matrix can be found by following the rule which we discussed before. The next question we have is whether when we have more than two or more than two Hermitian operator, then yeah, the question is whether we can simultaneously diagonalize those two Hermitian operators. And then the main reason we are interested in diagonalizing the Hermitian operator is related to the measurement in the quantum mechanics. In quantum mechanics, all the measurement is directly related to Hermitian operators, and then the result of the measurement is also related to the eigenvectors of the Hermitian operators. And then the more details will be discussed in later lectures. But I want to emphasize that if we can find out the common basis which can diagonalize two Hermitian operators simultaneously, then it will make the given problem much simpler. So there exists some theorem such that if two Hermitian operators are commuting with each other, then we should be able to find out the common eigenvectors basis composed of the common eigenvectors, and then that will diagonalize both of them. The proof goes in the following way. Before we start proving the theorem, let's think about the meaning of that theorem. What the theorem says is the following. So assume that we have the we know that each of the linear operator can have the matrix representation, and assume that we somehow have a basis which will represent this omega operator as the in the form of the diagonal matrix. So it will be omega 1, omega 2, omega 3, and so forth. And then all the off diagonal elements will be 0. And simultaneously, this lambda will also appear as the in the form of the diagonal matrix, something like omega 2, 1 to 3, and so forth. And then all the off diagonal elements will be again 0. Then what is the result of this product of two matrix? It will be as simple as omega 1, lambda 1, omega 2, lambda 2, and so forth. And all the, again, all the off diagonal element will be the same, will be 0. And in this case, even if we change the order of the multiplication, like this one, still the still the result of the product will be the same. So this is quite obvious that if the if two linear operators are are represented as the diagonal matrix, then the those two linear operator will commute with each other. What the theorem says is actually the other way around. What I mean is that in the theorem, what the theorem says is that if we know that two operators will two operator commute with each other, then we should always be able to find out this kind of basis, which will make the both of the linear operators appear in the form of the diagonal matrix. So let's prove such kind of theorem. And then to prove that, the theorem actually is valid not only for some special case, but it is valid for any kind of case, whether the linear operator is degenerate or non-degenerate. However, the proof for the general case is a little bit challenging. So instead of trying to prove all the cases, I will assume that at least one of the operator is non-degenerate. So assume that omega is non-degenerate. Then we can think about the one of the eigenvector of the omega. So in this case, that eigenvector will have the eigenvalue of omega sub I with this kind of relation. And then let's apply the that commuting operator lambda on the omega sub I. And the application of the some new operator on this vector will create new vector, which we will call as a V. And then um, in principle, this vector should not be parallel to omega sub I, or or yeah, so it might be some kind of arbitrary vector. However, what I'm going to prove here is that um, um, this one is actually the this new vector is also the eigenvector of the omega if the both the omega and the lambda commute with each other. Then how can we prove that? Well, the proof is simple. What we have to do is apply omega on V, and then we should be able to find out, we should be able to prove that this is, this will have some kind of this result. So how can we prove that? Well, we know that V is defined in this way, so we can replace that definition. Now we know that they commute with each other. So in principle, we can switch without any problem. And now, because of the associative property, we can first consider this part. Then this one is because of this relation, we can replace this one with the omega times omega sub I. And now this omega sub I is scalar, and this is operator. So scalar can move around. We can change the order of the scalar and the operator, in which case this will become omega sub I and the lambda omega sub I vector. And we know that this is the definition of the V. So eventually we prove that this one is omega sub I V. So what did we show? We started with this one, and then we proved that this is the same as this one. So we basically prove that this new v, v obtained by applying the lambda on the omega vector, this one is another eigenvector of the omega operator. So the story is not does not stop here. One more thing we have to also note it is that because we started with the assumption that the omega is non-degenerate, so what that implies is that um, because it is non-degenerate, and then we know that this new vector v has the eigenvalue of omega sub I. However, because it is a non-degenerate, this vector cannot be different from the omega sub I. Well, yeah, it can be actually a little bit different, but they can be different only by the length. But basically, the v and omega sub I should be parallel to each other, meaning that there will be some scalar value which will connect between these two vectors. And again, because we started with this definition, what this means is that this is omega sub I, and if you and can you recognize this relation? This is another eigenvalue problem. So what this means is that if the omega is and what this implies is that the omega sub I is also the eigenvector of the lambda operator. So what happened? So because what we did was we started with the assumption that omega and lambda commute with each other. Then the eigenvector and for the case of the non-degenerate um, operator omega, then the eigenvector of the omega is also the eigenvector of the lambda when they commute with each other. And for this case, I only showed that at least omega should be non-degenerate, but you can also do the general proof. Uh, you can also prove for the general case, and then such kind of thing is also discussed in the book. So I ask you to read the full proof in the reference. Next topic I want to discuss is the functions of the operator. And when if I talk about the functions of an operator, you might be wonder what I'm actually talking about, because you are generally familiar with the concepts of the functions of the numbers, but what do I mean by operator? Well, yeah, then before we move on, let's think about what kind of object can act on vectors. Well, the most simplest example is scalar value. Scalar value will just can be just p multiplied on the vectors, and then the scalar value and the operator can commute with each other. And we call in the quantum mechanics, we sometimes call the scalar value as a C number, because C means the classical number, and then classical number has no problem in exchanging the order of the multiplication. However, operator can also work on the can be applied on the vector, and the most obvious difference between the scalar value and the operator are that operator, the order of the multiplication of operator cannot be exchanged in general. Yeah, sometimes you can exchange the multiplication of operator, and then we call them, for that case, we call that two operators commute with each other. But in most of the general case, they do not commute with other operator. So in this case, even though this is not a number, we generalize the concept of the number, and we call the operator as the Q numbers. Then why do I discuss the C number versus the quantum Q number means the quantum number? Well, now, because now I want to think about the function of the Q numbers. Then, yeah, what do I mean by Q number? Functions of a Q number. Well, to generalize the concept of the function, then we should start with what we are familiar with, which is the C number, a function of the C numbers. So probably the easiest example of the C number function is that, such as the if we have x, f of x equals x2, then if we have the function of omega, then this will be very obvious analogy between the C number function and the Q number function. Then what about the sine x? So how can we define sine omega or log omega? Well, yeah, there is some hint, because as long as it is represented in terms of the polynomial, then we know that how to map this form to the operator. So why don't we start with the polynomial? So, and then there is a very powerful concept that, so if the C number function is already represented as the sum of the power series, then we can just replace this x with the operator. And yeah, in this case, we just define the function of the f as the, so yeah, for example, if we have to expand the sine of omega, then we will refer to the Taylor expansion of the sine function and replace each of the x with the omega. And then we know that most of the C number function can be expanded in power series via the Taylor series. So most of the reasonable function, or most of the practical function, can be represented as a function of the operator as well. Then, yeah, let's look at one of the most frequently used example of the function of the operator, which is the exponential function. And Taylor series of the exponential function is well known, like this one. Then when I'm talking about the exponential function of the operator, then this is the definition of the mathematical definition we will use very frequently in this class. And yet, mathematically, we should always make sure that all of the discussion will be valid only when the sum of the power series will converge to some definite limit. In the previous page, I didn't require that the operator used for the function should have any kind of property, but now, yeah, from now on, I will mainly limit our discussion for the function of the operator which is a Hermitian. Yeah, so function of the Hermitian operator will be our interest. Then Hermitian operator has a very useful property that the operator can be represented as a diagonal matrix if we use all the orthonormal eigenvectors as the basis for the matrix representation. Then we know that with this diagonal matrix, the square of the diagonal matrix is only just the squaring each of the diagonal components only. And if the mth order of the operator will be also replaced by the by a diagonal matrix, and its diagonal components will be just the mth multiply m times. Then we can imagine what will be the shape of the exponential function of the operator. And then exponential function is exponential function of the operator can be expanded in this way. And then this means that it will this omega should be replaced by the corresponding matrix representation, and that is because that is the diagonal term. So all we have to do is add each of these terms, multiply by this factor, and then if we just collect all the summation in the form of the matrix, then that each of the diagonal term will look like this one. And this one is very familiar shape of the exponential function. So eventually everything will just become like this one. And moreover, not only for the exponential function, but if we imagine that, if we assume that our operator, matrix representation of operator appears in the form of the diagonal matrix, then even for the some general, any arbitrary function, which can be expanded in terms of the Taylor series, then they will always look like this one. And then, yeah, even though, yeah, this was some specific example, you can see that this argument can be easily generalized for any arbitrary function. So in the eigenbasis, yeah, in the for the case of matrix representation in the eigenbasis, all the all the function of the operator will always appear in the form of the diagonal matrix, and then each of the diagonal component is the function of the corresponding eigenvalues, which is very convenient. However, you might also wonder that it's not usually so. In many of the situations, we cannot use the eigenbasis as the basis to represent some given operator in the matrix representation, because there are many different operator, and then unless those operator commute with each other, then you cannot choose the eigenvector eigenvectors which will simultaneously become the eigenvectors of all the operators. So that is kind of a limitation of this approach. However, there is very interesting concept. In the previous lecture, we learned that any arbitrary operator can be represented in different bases than original basis. And then what that means is that if we use the unitary transform, which will turn the original basis into a eigenbasis of the given operator, then the initial original matrix, which is the Hermitian matrix, which was not a diagonal matrix initially, can be turned into the diagonal shape. And then, yeah, such kind of transform can be achieved by using the unitary transformation. And then with this relation, we can also rewrite this relation into this form. Then the interesting property happens, because the square of the h squared means that multiplying this form together. However, we know that this pair of the unitary operator will just cancel to each other, and then becomes the identity operator. So it will just becomes like this one. And then if we multiply m times, then each of the this u dagger and dagger will be sandwiched between each of the d's, and then eventually they will all of those pairs will cancel with each other, and then eventually we will be left with d to the m, and then only the remaining first term and the final factor will be left. So we will always have this kind of shape. Then um, if we want to find out the function of some Hermitian operator, then this arbitrary function will be always expanded in the form of the polynomial equation, and then for each of the term, they will be replaced by this one. And then in this case, because all the terms in the summation will have the u factor and then u dagger factor in the end, so we can factor them in in this way. And then this one is simply the summation of the diagonal matrices. So the result of this summation will be another diagonal matrix, and then the value of this one is quite simple, like we saw in the previous page. And then all we have to do is multiply the u and u dagger at the end of the calculation. So yeah, this is the um, this is the very important property and very useful property of the Hermitian operator. And then fortunately, in quantum mechanics, we mainly use the Hermitian operator. So we can utilize this kind of property in the calculation of the uh, for, uh, for the calculation of the Hermitian operators. Up to this point, we discussed the function of operators. Then we might also consider the derivative of the function of the operators. And then how can, yeah, so assume that some operator depends on some parameter lambda. So this operator is a function of the function of this lambda. Then how can we find out the derivative of this operator with respect to this parameter? Well, mathematically, you might say that it is not well defined. So why don't we just define it? So my definition, or not only my definition, but general definition is the general definition of this derivative of operator with respect to the lambda will be in this form, which is the generalized form of the scalar function. So yeah, with this definition, then we can really think about calculating the derivative of some operator represented in the form of the matrix representation. Then we can think about this kind of situation. So how can we find out the derivative of exponential function of the operator when some of the operator is also multiplied by lambda? Then we know that this shape of the function implies that this kind of polynomial summation of the operators, and then we can even if, and then in this case, what we have to do is differentiate this sum with respect to the some scalar lambda, some parameter lambda, and then even if this operator is represented as a non-diagonal matrix H, still this expansion is valid, and within this expansion, then it is very simple, because all we have to do is just calculate the derivative of this polynomial, and then it will become like this one. And then you know that when m equals 0, then this is just a constant with respect to the lambda. So the first term will disappear. So that's why we start with the m equals 1. And then with this expansion, what we can do is because this one will cancel the m, so it will be the factorial of the m minus 1, and then we can just split this m to the h to the m to into multiplication of h and the multiplication h and h to the m minus 1. And finally, yeah, for this case, m is a dummy index, so we can just replace with n, and then yeah, we can make sure that the index starts from 0. In which case, it will turn into this shape. So now this is again the shape of the original exponential function of the operator. So we will have this kind of form. And then you note that this result is very similar to the scalar function. So for example, if we have exponential lambda a, which is just a scalar, then we know that because of the chain rule, yeah, we will obtain that the differentiation of this one will be left with this kind of situation. So even though this operator or matrix is replaced by the well, yeah, I can say the other way. Yeah, so even though this scalar value is replaced by the matrix representation, still the result of the differentiation of the scalar function is similar to the differentiation of the matrix function. So yeah, it's easy to remember. And then yeah, in general, we can say that the derivative of the exponential function of the operator will be actually just the exponential function by itself multiplied by the matrix when this exponent was the product of the scalar value and then the operator. Then why we were interested in the such kind of derivative of the exponential function? That's because we wanted to discuss about the this kind of differential equation. And why we are interested in the form of this differential equation? Because one of the most important differential equation or most important equation in the quantum mechanics is the Schrödinger equation, and this is the shape of the Schrödinger equation. In a typical situation, we are asked to solve this kind of differential linear equation when we are given some initial condition at time t equals to 0 with some kind of initial state. Then we are supposed to find out this kind of solution at a time equals t in terms of the initial state. And then the connection from the initial state to the final station will be made through some matrix element. And then typically, eventually, we will prove that this will be connected through some unitary matrix or unitary operator. So if you solve this kind of problem for the first time, probably yeah, you may not get exactly what this is trying to do. So let me give you a more concrete example. Yeah, so this example is not necessarily quantum mechanically correct, but this is a typical differential equation you might be provided in other typical situation. So let's say that this vector is some column vector, which I can just say that this is x1 and x2, and let's say that we have some matrix with this one, and then this one is connected to the current state through So the time derivative is connected to the current vector space state through some matrix. Then how can we solve this problem? Well, yeah, um, if you just don't think about the original form of the Schrodinger equation form, if you are just trying to, you are just asked to solve this problem, probably the simplest approach is that you will just start with the yeah, let me just not write the t part, yeah, because it is implicit, and then this one will be x1 plus 2x2 time derivative x2 is minus x1. And then to solve this equation, yeah, one option is we just do the second another time derivative for the entire equation. Then this one will become like this, and then we already have the relation for this one, so we can replace that one with minus x1. Then how do we solve this problem? Well, that's easy, because this is simply the second derivative differential equation. And in this case, we generally tried some ansatz for the solution form. So yeah, let's try with something like exponential st. Then this one will become c times a, and then you will have the common factor of c, and then s squared minus 3s plus 2, something like this one. And then yeah, you will have these common factors. And then yeah, the solution of this one is, yeah, of course, that is just like this. So it would have two s1 equals s equals 1 and 2. And so the general solution for this guy, yeah, which is x1, then the x1 general solution of the x1 is e to the t, s equals t plus, yeah, something like 2t. And once and then to find out the solution form of the x2, we can just use this equation. And then in that case, x2 is 1 over 2 by it's confusing. So then that is the x1 dot minus 3x1, which is a e to the t plus 2 times b 2b e to the 2t minus, so yeah, this was the time derivative of this one, and then minus 3 times 3a et minus 3b e to the t. Yeah. So this will be so they will be minus 2a times e to the t divided by 2. So minus a e to the t, and then this is minus b times e to the 2t divided by 2. So minus 1 over 2 b times e to the 2t. So we found out the general solution form of this one. Now we have to apply the initial condition. Yeah, so at time t at time t equals 0, then we would have x1 at t, and then yeah, for that case we would have this condition, and then for the x2, yeah, we would also have some value, and then at that time, at that point, it is minus b minus a minus 1 over 2b. Yeah, something like this. Then yeah, from this one we can immediately find that b can be 1 over 2. Sorry. 1 over 2b. Yeah, if we add both of the equations together, then the this A will cancel, and then only half of the B will be left, and then the left hand side we would have x1 0 plus x2 0, or we can just move this guy, and we would have this one. Then what about the A? Yeah, A can be found by multiplying 2 to the second equation and add them together. Then the minus A will be x1 0 minus 2 times x2 0, and then the we can just move that sign to the right hand side, so we would have this kind of solution. Okay. There was yep. No, actually, there was a mistake. Okay. So what I do was multiply 2 for the entire equation and add them together. So yeah, this it is a minus 2a, which is minus, and then it is a summation of this one and 2 times x2. And then now I can move this sign to the right hand side, which will become like this one. Okay, so yeah, now once we have everything correct, then I can rewrite from this relation. I can just rewrite the x1 of t is we can just plug in all those relation, and yeah, let me just do that by myself. So I would obtain by replacing a and b with this. I can obtain this one. Then we can collect x1 common factor. So then it is minus e to the t, and then the plus 2 times e to the 2t. And similarly for the x2 0, then it is minus 2 e to the t plus 2 e to the 2t. And similarly for the x2t, we would also replace minus a and minus b over 2 with this. Then we would have this expansion, and then again, yeah, if we rewrite in this way, we would obtain this result. And finally, yeah, let me rewrite this finding in the form of the matrix equation. So we would like well, yeah, no. So we want to write down this relation in the form of matrix. So we would have some matrix here, and then we would have x1 0 0 x2 0. So and then yeah, for x1, yeah, this part will go here, and this part will go here, and similarly this one will go here, and this one will go here. Now we can see that this final result is the form of the some final sum vector of as a function of the time is some product of the some operator or some matrix which is the which has the time dependence like this one, and then it is this matrix will be applied on some vector which is fixed at a time t equals 0. So now, yeah, so this is a very similar form to the final form which I was looking for before. So now, yeah, what what I want to do is find I want to convert the given differential equation, which was given here, this form into the relation into an equation for the u of t. So how can I do that? Well, that's relatively simple. What I have to do is, originally that equation was something like u of t, psi of t equals I omega psi of t. So instead of having this one, I just replace psi of t with the u of t psi 0, psi of 0. So by replacing that, I would have u of t psi 0, and I will also have this part replaced by u of t psi 0. And now we know that this time derivative will only work on this guy because this is fixed in terms of the time. So we know that, and then eventually each both of the term will have the this vector at time t equals time t equals 0 multiply from the right hand side. So we can also rewrite this equation in this form, minus I omega u of t, and this is multiplied by this initial condition or initial vector, and this u of t should be valid, should satisfy this equation, whatever the given initial condition is or initial vector is, which means that this equation by itself should be valid, or we can say that this one should have this form. And can you guess the solution of this operator differential equation for the operator? Well, we already saw this kind of relation, which was over here. So if you remember this one, then the solution of this equation should have the form of the u of the t. U of t should have the form of the exponential e to the I omega t. Yeah, so this is the very typical solution of the Schrödinger equation. And what this means is that the psi of t is connected to the initial condition at time t equals 0 through this kind of component. And in quantum mechanics, we call this one as a propagator because it propagates in terms of time. It propagates from the initial condition at time t equals 0 to some time t. And also another important property of this part is that as long as the omega is the Hermitian operator, then this exponential form of this one is actually the unitary operator. And that's why we are using the notation of u to imply that this part is always a unitary. And then initially, this might not be obvious, but if you remember that typically the role of the Hermitian operator is that um, uh, the role of the Hermitian operator is sorry, the eigenvalue of the Hermitian operator is the real value. So the Hermitian operator has some similar property with the real value, and then we know that exponential of the some real value multiplied by time t and then I, then we know that the absolute value of this one is 1. So this one has also the property that this kind of property is also related to the fact that the eigenvalue of the unitary is it is has the size of 1. So such kind of analogy between the real value and then the result of this exponential shape, and then the result the relation between the Hermitian operator and the unitary operator also exists. So for more detail, yeah, you should. I actually recommend that you should try to you should prove that the this kind of shape will always turn out to be unitary operator. So let me finish today's lecture at this point, and then we will continue from the discussion of the more solution of the um, uh, solution form of the Schrödinger equation.